Jai Hind, dear students. Today in this lecture we will see the how we can find the solution of state equation, and second we will see the diagonalization method. So first of all we will start with the solution of state equation. So as we know, the state equation we can write as x derivative is equal to ax plus bu, and the output equation we can write y is equal to cx plus du, right? So this is the we can say this one is the state equation. This is our state equation, and this one is our output equation. Right? So we have to find the solution of this state equation. Now in this we will take two cases. First we will take the homogeneous case, or the solution of homogeneous state equation. The solution of homogeneous state equation. Right. So in this case we will assume that u is equal to 0. So this state equation can be written as x derivative is equal to ax. So this is the homogeneous state equation, and we can also write it as derivative of xt with respect to dt is equal to a into xt. Okay. The solution of this state equation should be, or this differential equation should be, xt is equal to e to the power at into x naught. It should be the solution, but we will see how we can find this solution. Okay. So here this e to the power at, this is the exponential term, and we can represent it as, we can write it as e to the power at is equal to I plus at plus a square t square divided by factorial 2 and so on up to infinity. So this is the expansion of e to the power at. Now the solution that we have assumed is xt is equal to e to the power at into x naught. If I put the value of e to the power at in this equation, then it will be I plus at plus a square t square by factorial 2 and so on into x naught, right? This is xt. Now if we differentiate this equation, we will get dxt over dt is equal to, if I differentiate this, then differentiation of this I will be 0, and differentiation of this with respect to t will be a, plus this will be a square into t. Then next term we will have a cube into t square divided by factorial 2 and so on into x naught. Okay. Now we can take a common. So if I take a common from this, then it will be I plus at plus a square t square by factorial 2 and so on into x naught, right? Now this is what? This is nothing but e to the power at. So I can write it as a into e to the power at into x naught, right? And this is derivative of xt with respect to t, right? So if I assume this is my equation number 2 and this one is my equation number 1, so if I compare these two equations, what I will get? I will get a xt is equal to, after comparing equation 1 and 2, so compare equation 1 and 2, what I will get? I will get a xt is equal to a e to the power at into x naught. So it will give xt is equal to e to the power at into x naught. So it signifies that this is the solution of the homogeneous state equation in which we have considered u is equal to 0, right? Here this e to the power at is called state transition matrix. Very, very important term, state transition matrix, and it is represented by phi t. This e to the power at we represented by phi of t, right? So the solution of homogeneous state equation we can write xt is equal to phi t into x naught. So this is the solution of, we can say, final solution of homogeneous state equation. Now in second case we will take the non-homogeneous equation and then we will try to find the solution of that. Okay. Second case is the solution of non-homogeneous state equation. Non-homogeneous state equation, right? So in this we can write the state equation x derivative is equal to ax plus bu, or we can write it as derivative of xt divided by dt is equal to a into xt plus b ut, right? I can further write it as derivative of xt divided by dt minus a xt is equal to b ut. Okay. Now pre-multiply this equation by e to the power minus at. So we will pre-multiply by e to the power minus at. So if I pre-multiply, then I can write it as e to the power minus at into derivative of xt with respect to t minus a xt is equal to e to the power minus at b ut. Clear? Now consider this term. Okay, if I differentiate e to the power minus at xt, then what I will get? So first if I differentiate this, so it will be minus a e to the power minus at into xt, right? And plus e to the power minus at into derivative of xt, right? So I will get this. So if I multiply this e to the power minus at inside the bracket, then it will be e to the power minus at dxt by dt minus e to the power minus at into a into xt is equal to e to the power minus at into b u of t, right? So this term and this term, these two terms are equal, right? Here I have minus a e to the power minus at xt minus a e to the power minus at xt, then I have e to the power minus at dxt over dt, then second term is e to the power minus at dxt over dt. Okay, so I can replace this term by derivative of e to the power minus at xt. So I can replace by this. Okay, so I can write this as d by dt of e to the power minus at into xt is equal to e to the power minus at b u t, right? Now if I integrate this equation, what I will get? E to the power minus at xt is equal to x naught plus integration 0 to t e to the power minus at b u tau d tau, right? Now it can be further written as xt is equal to e to the power at into x naught plus 0 to t e to the power minus a t minus tau be u tau d tau, right? Now, in previous case, we have assumed that this e to the power at, we can write it as phi t, okay? So, here in this equation, if we can modify, then we can write phi of t into x naught plus 0 to t phi t minus tau be u tau d tau, right? So, this will be the solution of non-homogeneous state equation. In this equation, on right hand side, this first term is representing the natural response, or we can say zero input response, and this second term is representing forced response, or we can say zero state response, right? So, this is the solution of non-homogeneous state equation, right? So, this is the conventional method to solve this, or we can say this is the time domain method. The same solution we can find by using the Laplace transform method, okay? So, second we will see how we can find this solution by using the Laplace transform, okay? So, we have state equation x derivative is equal to ax plus bu, or we can write it as derivative of xt is equal to axt plus but, right? So, if I take the Laplace of this, it can be written as s into xs minus x0 is equal to a into xs plus b into u of s. Okay, so now I can take this term to this side, so it will be si minus a into xs, and this term I can send it to this side, is equal to x naught plus b u of s, or this x of s will be si minus a inverse of x naught plus si minus a inverse of b of u of s. Now, we assume that this si minus a inverse is nothing but phi of s, okay? And if I take the inverse Laplace of this, then I will get phi of t, okay? And phi of t is nothing but e to the power at, or we can say it is our STM, state transition matrix. So, this equation can be modified as x of s is equal to phi of s into x naught plus phi of s into b u of s. Or in time domain, if I take the inverse Laplace of this equation, in time domain I can write xt is equal to phi of t into x naught plus 0 to t phi t minus tau b u tau d tau, okay? So, again the same solution we can find using the Laplace method. So, this is the way how we can find the solution of state equation, okay? So, in previous case we have seen in time domain how we can find the solution of non-homogeneous state equation, and in this case we have used the Laplace transform method, okay? So, now we have the key term state transition matrix, state transition matrix, right? Now, we will see the methods to find this STM. That is, if we want to find the solution of state equation, then we need state transition matrix, and what are the various methods by which we can calculate the state transition matrix. So there are basically 4 methods. In this lecture we will discuss only one method. So there are 4 methods. One is infinite series method, infinite series method. Second is Laplace transform method, Laplace transform method. Next is Cayley-Hamilton, Cayley-Hamilton theorem. By using Cayley-Hamilton theorem we can find the state transition matrix. And last method is diagonalization method, diagonalization method. So in this lecture we will see how we can find the STM using this diagonalization method. Okay, so we will discuss this. So diagonalization method to find the STM or state transition matrix. So this method we can apply if the matrix A, because state equation we always be, it will be in the form of x derivative is equal to ax plus bu, and output equation will be y is equal to cx plus du. So in these equations always we will have the value of a, b and c and d generally. Okay, so if matrix A is given in this form, lambda 1 0 0 lambda 2, that means if it is a diagonal matrix, okay, then how we can find the state transition matrix. Okay, so we will see. So as we know, e to the power at can be written as I plus at plus a square t square by factorial 2 and so on. If I put the value of a, then it will be e to the power at is equal to I can write 1 0 because it's an identity matrix, so I can write it as, so next we will put the value of a, so lambda 1 0 0 lambda 2 into t plus a square, that is lambda 1 square 0 0 lambda 2 square into t square by factorial 2 and so on. So if I solve this, I can write it as 1 plus lambda 1 t plus lambda 1 square t square by factorial 2 and so on. This will be the first element, second element will be 0, third element will be 0, and fourth element will be 1 plus lambda 2t plus lambda 2 square t square by factorial 2 and so on. Okay, and it can be written as e to the power lambda 1t 0 0 e to the power lambda 2t, right? So this will be the value of e to the power at. So by this way we can find the state transition matrix. So this is the simple method. If matrix A is given in the diagonal form, we can use this method and we can find e to the power at, that is STM or state transition matrix. So there is no problem in this, but the problem will arise when this matrix A is not in the diagonal form. If it is not a diagonal matrix, then how we will use the diagonalization method to calculate the state transition matrix. So we will see it by an example. In this example we will take, let A is equal to 1 4 minus 2 and minus 5. For example, A is this matrix, okay, and we have to find e to the power at. We have to find e to the power at, that is STM, or we can say state transition matrix. Okay, so we will see how we can use the diagonalization method. Okay, so first of all we will calculate the eigenvalues and then we will calculate the eigenvectors. Okay, and then we will see how we can calculate the state transition matrix. Okay, so first of all we will find the eigenvalues for this. So for eigenvalues we will write lambda I minus a. So determinant of this should be is equal to 0. Okay, so this will provide the eigenvalues. So if I calculate lambda I minus a, so lambda I minus a will be is equal to, I can write it as lambda 0 0 lambda minus a is 1 4 minus 2 and minus 5. Okay, so this will provide lambda minus 1 minus 4 and 2 and lambda plus 5. Okay, if I take the determinant of this matrix, it will be lambda minus 1 into lambda plus 5 and plus 8 is equal to 0. After solving this, we will get lambda square minus plus 5 lambda minus lambda and minus 5 plus 8 is equal to 0, and lambda square plus 4 lambda plus 3 is equal to 0. After solving this, I will get lambda 1 is equal to minus 1 and lambda 2 is equal to minus 3. So these will be the eigenvalues. These will be the eigenvalues. Okay. Now, corresponding to these eigenvalues, you can find the eigenvector. Okay. So, the eigenvector corresponding to the first eigenvalue minus 1. So, I can write lambda 1 into I minus a into x1 is equal to 0, where x1 will be, this x1 will be m11 and m21. Okay, so I can write lambda 1 is nothing but minus 1 into I is 1001 minus a is 1 4 minus 2 minus 5. Okay, into x1 I can write m11 and m21 is equal to 0. So now if I solve this, I will get minus 1 0 0 minus 1 into minus 1 4 minus 2 minus 5 and multiplied by this m11 and m21 is equal to 0. Then after solving this, we will have minus 2 minus 4 and 2 and 4 multiplied by m11 m21 is equal to 0. And if I convert it into equation form, then I will have minus 2 m11 minus 4 m21 is equal to 0, or second equation will be 2 m11 plus 4 m21 is equal to 0. Now here we assume, or let m11 is equal to 1. If I select m11 is equal to 1, then m21 will be is equal to minus 0.5, right? So this I have obtained m11 m21, it is equal to 1 and minus 0.5. Similarly, we will find the eigenvector corresponding to the eigenvalue, that is lambda 2. Lambda 2 is equal to minus 3. So in second case, we will write lambda 2 into I minus a, this into x2 is equal to 0. Here x2 will be m12 and m22, right? So this will be minus 3 0 0 minus 3 minus 1 4 minus 2 minus 5, right, into m12 m22 is equal to 0. Okay, after solving we will get minus 4 m11 and minus 4 m22, right, is equal to 0, or from here we can get plus 2 m11 and plus 2 m22 is equal to 0, or if I assume, sorry, it is m12, M12, okay, M12, M22. So if I assume M12 is equal to 1, then M22 will be minus 1. So the second eigenvector is M12, M22 is equal to 1 and minus 1. So finally what I will get, I have calculated the model matrix M is equal to M11, M12, M21, M22. So this is called the model matrix. So here I can put the values. So it is 1 minus 0.5, again it is 1 and minus 1. Okay. Now I will calculate M inverse. Okay. So M inverse we will calculate, and the value of M inverse will be 2, 2, minus 1 and minus 2. Okay. So this will be the value of M inverse, right? Now we will calculate the capital lambda. Okay. What is capital lambda? Capital lambda can be given as M inverse A into M. So I will put the value of this M inverse. It is 2, 2, minus 1, minus 2. I will put the value of A here. A is 1, 4, minus 2, minus 5. Okay. And then I will multiply it by M. M is 1, 1, minus 0.5 and minus 1. So after multiplying this, I will get capital lambda is equal to, capital lambda will be 1 minus 1, 0, 0, minus 3. So with the help of this, I can find e to the power capital lambda t. So obviously it will be e to the power minus t, 0, 0, e to the power minus 3t. Okay. Now I can find e to the power at. E to the power at will be m e to the power capital lambda t into M inverse. Okay. So I can put the value of M. It is 1 minus 0.5, 1 minus 1 into e to the power e to the power minus t, 0, 0, e to the power minus 3t into M inverse is 2, 2, minus 1, minus 2, 2, 2, minus 1, minus 2, right. So after multiplying this, we will find the final value of e to the power at, and it will be 2 e to the power minus t, okay, 2 e to the power minus t minus e to the power minus 3t, 2 e to the power minus t minus 2 e to the power minus 3t minus e to the power minus t, and I think plus e to the power minus 3t, and finally it will be minus e to the power minus t and plus e to the power minus 3t. So this will be the final value of STM, or state transition matrix. Okay. So this is the way how we can use the diagonalization method to find the STM. Okay. So theory behind this numerical we will discuss in the next lecture, but you can see this diagonalization method can be used to find the STM. So in this lecture we have discussed the solution of homogeneous and non-homogeneous state equation, and then we have also seen that how we can find STM using the diagonalization method. Okay. So we will stop here.